Okay, so now to compensate a bit the previous lecture, which was rather heavy on details, I'm going to talk about lazy learning, which, as the name suggests, is a bit simpler. So I'm going to start by explaining what lazy learning is and in which way it differs from eager learning, what we've been seeing so far. And then I'm going to give a few examples. K-nearest neighbors can be used for classification or for regression. Kernel regression, which is another lazy learning approach to regression, and also kernel density estimation, which is neither regression nor classification, but focus on trying to estimate distributions of values. So the idea here is that what we've been seeing so far were examples of eager learning. Eager because learning is done at the beginning. So we have a model that represents the hypothesis class, and we present the training data to the model in order to fit the parameters. Once these parameters are fit, that we have the model trained on the training data, we can then just ignore the data and answer any future queries based on those parameters of the model, or basically on the hypothesis that we selected. With lazy learning, we don't do a training step. So basically, we may not even have a model to represent a hypothesis class. We don't need to have any parameters that we need to optimize. We just retain the data, store the data, and then when we need to answer some query, we look up the data and do the computations at query time. So this is why it's called lazy, because there is no actual training step first. Basically the process is not to do anything with the training data, except when somebody asks a question, asks to classify or predict some value, and then we look at the data and see what we can tell. So let's see an example with the k-nearest neighbors classifier. The general approach here is to keep all the training set. We just store it in memory. And when we are asked to classify a new point, we find the closest k examples in the training set, and we predict that the new point has the same label as the majority of those k examples in the training set. So this is lazy learning. We don't need a model. We don't need to fit parameters to the training data. We just store everything, and only when we are asked to predict a new value, we're going to look at the data and make our prediction. So basically, if we are doing k-nearest neighbors with k equals 1, this means that we are going to look at the training data for any future prediction, look at the training data and predict that the new point will have the same label as the closest one in the training data. So this will result in what is called the Voronoi tessellation, which is basically, if you use Euclidean distances, it will separate the classes at the midpoint of any pair of points that are closer together. So for example, this frontier here is at the midpoint between this red point and this blue point. So if a new point falls here, it's closer to the blue point, and the classifier predicts it will be a blue point. If it falls on this side, it is closer to this red point, so it predicts it to be a red point. So each point will have its own area where any new points that fall in that region will be closer to that particular point, and so will be assigned the same label as that point. Of course, k equals 1 is often not very reliable. We can use larger neighborhoods. For example, k equals 3, k equals 5. This will give us more complex tessellations, but the idea is the same. So in this case, if a point falls here, we find the 5 nearest neighbors, and since the majority of those are red, any point falling here will be classified as red. If we fall here, then the 5 nearest neighbors will have a majority of blue, and so the point will be classified as blue, and so on. So this is the k-nearest neighbors algorithm. Note that we don't need to train anything, because we are not fitting parameters in a model. We just store the data. This is the training data, and these will be the predictions for any new point outside the training data, depending on where it falls relative to the points in the training set. In all these cases, if we use this Euclidean distance, the decision boundary is piecewise linear. That is, it is formed of straight segments that correspond to those differences between having a majority of neighbors of one class or a majority of neighbors on the other. If we increase the value of k, that is the neighborhood that we are considering, the frontier, the discriminant, becomes less dependent on local conditions. For example, suppose that this is the training set, so we store all these points and we separate the two classes based, for example, on k equals 1, k nearest neighbors. This means that the classification of blue or red is based solely on the class of the nearest point. So on this side, it's all the blue points, on this side, the red ones. If we increase k, for example, 25, in this example, then the classification, the prediction we have is based on the majority class of the nearest 25 points. So for example, for a point here, there are some blue points in the neighborhood, but there are lots of red points in the neighborhood. So the nearest 25 points have a majority of red examples, so here it's classified as red. In this place here, for example, is classified as blue because the majority of the 25 nearest points are blue. So if we increase the value of k, we make the frontier, the discriminant, less dependent on what exactly are the points nearby and make it look further away for the majority of points in the neighborhood. Okay, so to implement a k-nearest neighbor classifier, first we need to measure distance between points, because in order to find the k-nearest neighbors, we need to have some measure of distance between any new point and the points that we have in the training data. If we have categorical data, for example, features that are classes, we can have different classes, for example, professions or types of sports or things like that, that are not a continuous value. We can use something like Hamming distance, which is the sum, the distance between two vectors with categorical data will be 1 added for each category that is different and 0 if it's the same. So two vectors that have exactly the same category are at 0 distance from one another. If they are all different categories, then we just add 1 for each feature and so on. If we have continuous features in our data, then we can use a general distance measure like Minkowski distance. This is a generalization of distance measures where we are going to add for all the pairs of features from one point and the other, the absolute value of the difference raised to the power of p, and then we are going to take the p root of that sum. So if we are using p equals 2, this is Euclidean distance, the one that is most used perhaps. If we use p equals 1, this is Manhattan distance, is the one that you count straight up or to the left or right and so forth. So just to give an example, with the Minkowski distance with p equals 2, this is Euclidean distance, you get something like this with k equals 1. If you have, for example, p equals 1, you get this sort of frontiers because now you're adding distance along each direction upwards or left, right, so vertical or horizontally. But you can use fractional values for p, so all of these are mathematically distances, although then things can be quite weird. So basically you need a measure of distance, but the measure of distance does not have to be Euclidean. In some cases it may be more useful to have different distance measures, and the frontier will depend on exactly how you're measuring the distances between the points. Okay, so first we need the distance. We can generalize this. We can create a function for the Minkowski distance of one point to a set of points in our training data. So basically this this uppercase X is our training set, the features of our training set, and this lowercase x is a new point that we want to classify. And here we can use a default p-value of 2 to make it by default the Euclidean distance. So if this is the Euclidean distance, then we get the square of the difference, like this here, the square of the differences. We add the square of the distances and we take the square root. Of course, for generalizing for p, this is taking the power p and then the power 1 over p for the root, and we can do that with the numpy power function. So basically, this will tell us the distance between one point and all the points in our training set. This returns a vector with all these distances, and we can use different distance measures if we want. Now that we have the distance, we need to find the k nearest neighbors. So the k nearest neighbors, the indexes of the k nearest neighbors, is simply the result of getting the indexes that sort the distance. So argsort in NumPy tells you what are the indexes that sort an array in increasing order. So starting from small to large. In this case, it will tell us the closest neighbor is the index of the one with the smallest distance. The second closest is the index of the second one, and so forth. So if we want the k closest neighbors, the k nearest neighbors, we need these indexes, but only the first k elements. So this is the function that measures the distance between this point here to all the points in our data set and returns the indices of the points in our training set that are closest to the point we are querying. And now for the classification, we get the closest neighbors, so the nearest neighbors, the k nearest neighbors in our training set, and we return the mode of the labels for those neighbors. Now the tricks, there's something tricky here, is that when you use the mode function from SciPy stats, it actually returns several things. It returns one array with all the modes, so the first one is the most common value, the second one is the second most common, and so on, and an array with all the counts. So we need to use only the first array because we want only what the values are, and we want only the first of those values because that is the most common value of all. And if we do this with our classes, what we get is the most common label inside this k neighborhood. So the neighborhood formed by the k nearest points. And this is what we want for classification. So basically, it's very easy to implement a k nearest neighbor classifier. You don't need to implement it because you have it on scikit-learn, but this is just to show you the actual algorithm so that it's easier to understand in detail what we're doing. Now, one question here when we're using distance functions is about rescaling, what we did with standardization, normalization, and so on. In general, you should rescale the data because imagine that one of your features was salary in euros, the other feature was age in years, and so on. It makes no sense to make a correspondence between €1 and 1 year when computing distance because those units are not even the same kind of thing. So we should not think that the distance of 1,000 euros is larger than the difference of 1,000 years or something like that. So in general, when you have different physical things or different features that are referring to different things, you should rescale the data and put everything, for example, with a zero mean and the standard deviation of 1, so that everything counts more or less at the same scale. However, there is an exception. For example, suppose that one of the features was distance to the east and another feature was distance to the north. And if you rescale things, you may be distorting the actual distance measures if it happens to be the case that there are more points far away to the east and to the north, and so everything gets distorted. So in general, you should rescale everything and do the standardization or normalization that we've been seeing so far, but be careful when the different features actually represent the same physical quantity. You may not want to distort them relative to one another. So in general, yes, but it depends on the problem. Now, to find the best value of k, we do the same thing as always. We can do cross-validation and we can try to find which one results in fewer mistakes outside the training set. So cross-validation, we can test for different values of k. We're only going to use odd values of k when we have binary classification, because that makes it simpler since it avoids having a tie. If you use a k of 4, for example, and you want the majority class in the 4 nearest neighbors, if 2 of them have one class and 2 have the other, the result is ambiguous. So if you ask for the majority of the 5 nearest neighbors, you don't have that problem. Of course, if you have a classification with more than 2 classes, then this problem will appear eventually. But for 2 classes, we can avoid ties if we use only odd values. So one important thing is that we cannot use the test error for making any decision. If we use the test error for making a decision, we are going to bias that estimator. But we can plot the test error. So in this case, I'm plotting the error on the training set and the validation for cross-validation. So these are averages over the different folds, exactly like we did before. I'm also plotting the test error in each case. I can do this. This is not a problem, as long as I don't choose this one because it has the lowest test error. Because if I decide to choose this value for having the lowest test error, then I'm biasing the test error in this case. Okay, so I should use validation, cross-validation to choose, and the test error is just an unbiased estimate of the true error. Okay, so here we can go look at the cross-validation plot. We can choose the best one here, and then we train with the full training set, and we compute the test error, exactly like we did with the logistic regression a while ago. Now, one problem that we have with these methods based on distance, and in fact it often occurs in general, but it's more problematic usually when we are based on distance, is called this curse of dimensionality. So imagine that you have one-dimensional data, just one feature, and we consider that the edge of our group is about 5% on each side. So suppose that you have this line here, and you take 5% on one edge, 5% on the other, and that's the frontier of your data. If you extend this to 2 dimensions, then you have a circle, and the edge, if the width of the ring is again 5%, now the area it occupies is 10% of the circle, because now you have a wide ring all around your circle. If you go to 3 dimensions, then you have a shell, and it now is 14% of the area. In 4 dimensions, we can no longer imagine it, but it's even worse. And basically, if you plot this, a frontier of 5% in this dimension, in 1 dimension, in about 20 dimensions reaches about 70% of your data. So the problem here is that when we are considering frontiers here, so suppose the frontier, we are considering a small margin of error there, which is around 5%, let's say. If we have the same kind of data, but in 20 dimensions, then 70% of the points will fall inside that frontier, approximately, if we assume the same kind of distribution. So this is the curse of dimensionality. If you have too many features, too many dimensions, then everything will start getting on the frontier, and you'll start making a lot more mistakes. So typically, we should try to do something to reduce the number of features if we have many features. We're going to see something about that on the second half of the semester, but I just wanted to mention here, for this first part, we're only going to look at data with 2 features. In the assignment, maybe you'll use more features, but for the examples, I only use 2 features so that I can show the plots. But in general, you can have in real life examples many features, and this can cause problems due to this curse of dimensionality. So let's see how we can use k-nearest neighbors for regression. We can do the same thing looking at the k-nearest neighbors, but instead of predicting the majority class, we can predict the average of a continuous value. So suppose that we are doing this regression with the usual points that we use, those that curve. We can just use a k neighborhood and take the average of the k nearest values. For example, with k equals 1, we have these steps here because we always take the value of the nearest point in our training set. So if we want to predict the value here, the nearest point is there, we take the same value and move on in that way. If we increase the neighborhood, then we start averaging over the points surrounding each prediction that we want to make, and we can have something that is a bit more smooth. And so on as we increase the neighborhood. Okay, so one thing that we can note in this kind of classifiers or regression with k nearest neighbors is that if we use a k that is very low, we are looking at the data that is very close to the point. For example, in this case for classification, if we use a k of 1, we are looking at the closest neighbor for the class label. If we are doing regression with a k of 1, we are looking at the closest neighbor for predicting the continuous value. So this means that in general, we will find the greatest overfitting at small values of k. Because if you use a k equals 1, you generally have 0 training error, because each point will be the neighbor of itself, and unless you have points that are overlapping and have different values, each point will always have the correct value for predicting its own value. So we tend to get a training error of 0 when we use k equals 1, and this will result in the greatest overfitting, because now we are only looking at the closest value. This regardless of whether we are doing classification or regression. The problem is the same because we are only looking at the closest value here. It's as we increase the size of the neighborhood, then we start lowering the ability of the model to, or we don't have it exactly a model, but lowering the ability of this classifier or regression to adjust too much to the training set. So we start getting into underfitting when we look at very large neighborhoods. So this is basically an inverse of what we usually see when we are, for example, increasing the degree of the polynomial or the expansion in the logistic regression and so on. So pay attention to this profile and try to understand why the training error is lowest when we have a smaller k and the validation error is highest when we have a smaller k. Now, one problem with the k nearest neighbors for regression is that we have all these stairs here as we change the neighborhood. We have discontinuities when we change from one neighborhood to the other as we move along the line. We can avoid that by doing regression in a different way. This will also be lazy learning, but we can use a kernel function to weigh the different points in a continuous manner. So a kernel function in this context, we will see this name appear again in a different context with a different meaning, but in this context here, a kernel function is a function, a continuous function with these properties. It has to be non-negative, so at all points this kernel function is at least 0. The total area of the function, so the integral, is 1, it has a unit area, and it's symmetrical. It means that the value of the function for u is the same as the value for minus u. There are many different functions that have these properties. Here are some examples from Wikipedia. You have this Gaussian function, this rectangle here, the triangle, things like that. So all of these fulfill these conditions, have an area of 1, are all 0 or higher, and have and are symmetrical. So they are the same on the positive side and the negative side. And now we can use these functions to give different weights to points as that are farther apart or closer to the point we want to predict. So in order to use kernel regression, we need two things. We need the kernel. Let's use a Gaussian kernel, for example. This is the expression for this Gaussian curve here. And we need an estimator, which is a function that weighs the different points in our training set differently in order to give a prediction. For example, the Nadaraya-Watson estimator gives us a weighted average of all the points in the training set, so these are the n points in the training set, as a function of the kernel with the input divided by this hyperparameter here. So the idea is that each of the points in the training set has an epsilon value. For example, these points here, the red points, all have an x and a y value here. And now if we want to predict the value for the regression at a specific value x, we want to predict the value y there, we're going to gather contributions from all the points in our training set, but with a weight that depends on the kernel. And the kernel, the input to the kernel is the difference between the point we're trying to predict and each point in our training set. So if we use a kernel that is shaped like this, it will give a weight of nearly 0 to points that are far away, but points that are close together will have higher weights. So we will pay or give more weight to the points that are near the one we're trying to predict, and less weight to the ones that are further away. And this is just the sum of all the weights, so this is a weighted average. There are other estimators. For example, Priestley-Chow uses also the different weights depending on the distance between the spacing of the points along the data set, but this is mostly for time series and things like that, so we're going to use this simpler one, more generic. But there are many other estimators. If you want to do kernel regression in some real applications, you should take a look at the different estimators to pick the one that is more adequate to the actual problem that you're trying to solve. So let's just implement these two. This is the Gaussian function. So this is just a transcription of this expression here. So e raised to minus 1/2 of u squared divided by the square root of 2 pi. This is the function for the Gaussian curve. And this is the Nadaraya-Watson estimator. So we can receive in Python any object as an argument. And in this case, this function is receiving another function as an argument. So we are calling the other function here, which is the kernel. We are inputting to the kernel the difference between the point at which we want to estimate the new value, or this can actually be a vector of points. Note that NumPy allows us to do these kinds of operations with scalar values, so this u can be just a number, or with vectors, with arrays of values. So this u can be a vector with a lot of numbers for which we want to compute something. So now for each point in our data set, we're going to compute this u value for the point or points at which we want to make the prediction. We divide the difference between the two by this h parameter. We input that into the kernel, and then we use the output of the kernel in this weighted average here. Okay, so now we can check the result, and we see that this h parameter here will make the regression very different depending on what value we give it. Because if we have a very large h here, or in this expression, this means that we are dividing the difference between the position of the point we want to estimate and the points in our data by a large number, and this makes the input to the kernel smaller, so that all the points, even if they are far away, will still count for something. And this is what the effect that this has, is to make it as if the Gaussian function was broader, and we get a smoother curve because we are looking at points that are farther apart. If we do the reverse, if we shrink the value h, make it smaller, we are giving more weight to the points that are close to each estimate we want, and less weight to the points that are farther apart. So this makes the curve more adjusted to the actual data and less smooth. So basically, by controlling this h value, we can adjust the smoothness of the regression we are doing and make it approximate the points more, or be more conservative and not to curve so much. Another thing that we can do with kernels is to, instead of doing this kind of regression, which is supervised learning, we can do estimation of the density of distributions. So this is an example of unsupervised learning. We're going to look in more detail at unsupervised learning examples in the second half of the semester, but this is just a very simple thing to do once you understand this idea of using kernels, which is to get an estimate of a distribution of values. Suppose that we have these values here represented by x. So we have some here, then a greater concentration here, and then fewer on this side. We could try to estimate the distribution parametrically. For example, we compute the mean and the standard deviation, and we assume a normal distribution or Gaussian distribution, something like this, with the greater concentration here and smaller there. That would be one way of estimating the distribution. Or we could use histograms. For example, we could count how many are in this region here, and we have one here, one, then 3 or 4 or something like that, and all the way to 25 and so forth. Okay, so we have this green histogram here, or we could make the bins a bit wider and we could have this yellow histogram here. But note that all of these distribution estimates either assume something about the distribution, for example, assume that it is Gaussian, or are discretizing the distribution, in this case in the histograms, by counting at different bins, and this will give us very different shapes depending on the size of the bins that we use. With kernel density estimation, we can do this in a continuous fashion by counting the contribution of each point, not as a discrete contribution on some place, but as a continuous contribution spread out using a kernel function. For example, with a Gaussian function, a Gaussian kernel, we can spread out the contribution of this point over this area here, and do the same for the other point, and so on. And when we plot the sum of all these Gaussian curves, we have this kernel density estimation, this curve here, that will give us the contribution of all the points to the overall distribution, but in a continuous manner, and one that does not depend on assuming some shape for the distribution, like we do when we assume, for example, a Gaussian distribution. So in scikit-learn, it's easy to use to do kernel density estimation, because you have this kernel density object that you can create, and it works the same as classifiers and regression models. You just do the fit, but in this case it's unsupervised learning, so you don't have actual labels, you just fit the values of the features, and it will give you the distribution of those using kernel density estimation. So then you can, if you have a new set of points where you want to evaluate, for example here at this point we want to evaluate the density of the distribution, then you just you add as an argument the new set of points to the score samples method after fitting, and this will give you the density. Actually, it gives you the logarithm of the density, because this is more useful when you're dealing with probabilities, where often you need to multiply probabilities, and if you have very small numbers, the multiplication will tend to underflow. So if you use logarithms, you can just add the logarithms, and it makes everything numerically more stable. But you can also, if you take the logarithm and you want to plot the chart, you can just raise e to the logarithm, and you get the actual probability values. So for sorry, this should be summary, not regression. But to sum up this part, we saw this difference between lazy learning and eager learning. In eager learning, we start with a training process that will try to extract as much information from the data as the model can, to adjust all the parameters and produce a hypothesis. After that, we don't need the data anymore. We have the hypothesis, and we use the hypothesis to predict new values. With lazy learning, we just store the data, and when we need to predict some value, we look up the data, for example, looking at the nearest neighbors, or using the kernel function to compute the value at some point we want to predict, and so on. So these are examples of a different approach. where we don't have to train a model first and to fit the parameters. We also saw this idea of the curse of dimensionality. So in all the examples I'm going to give in general, I'm going to use a low number of features so that I can do the representations, plot the charts and so on. But in real life applications, you usually have a large number of features. And if you have a large number of features, things can get complicated because with a large number of features, it's hard to distinguish between different groups because the frontier will now encompass most of the data that you have. And we saw these k-nearest neighbors regression, kernel regression, and density estimation. So for lazy learning, I recommend that you look at these sections here, and just give me 2 or 3 minutes and I'll start the Zoom meeting if anyone has questions. Okay, see you soon.